So here's our setup. We have this whiteboard that I've cut a hole in the center, and I've dropped a string through the center, and then on the end of the string is a rubber band connected to a puck made out of dry ice. So I took a chunk of dry ice and I cut out a round cylindrical hockey puck sized piece of dry ice that now slides very well on this whiteboard, and I put the string through the hole and attached a weight to the end of the string that pulls downward underneath the table, producing tension in the string. And then I spin with my hand, I spin the puck around the table. Now watch as it spins. Even though the surface is very slippery for the dry ice puck, there is a small amount of friction, so eventually the puck does begin to slow down. And so as the puck slows down, you'll notice the radius of the circle becomes less, becomes smaller.
Let's apply our equation for Newton's second law for uniform circular motion to this situation. The centripetal force is equal to mv squared over r. The centripetal force, we know, is provided by the hanging weight. That is not changing, so the centripetal force, which is the tension in the string provided by the hanging weight, is constant. It doesn't change. So that means the right side of the equation must also remain constant. So as tangential velocity decreases, as we saw from the slight friction between the puck and the whiteboard, so too then must the radius also decrease to keep this fraction a constant, just like the centripetal force.
This time I'm going to reach under and pull on the string and cause the string to get shorter. I have increased the centripetal force, forcing this radius to get smaller. At the same time, we can see the speed of the puck is increasing.
Let's analyze this with Newton's second law. As I pull on the string, I increase the centripetal force. As the centripetal force increases, the radius decreases, and the tangential velocity increases. I know that the tangential velocity increases because when I pull on the string, I am doing positive work, and I'm adding kinetic energy to the system.
Here we see a ride at an amusement park in which chairs hang from chains, and the ride begins to spin around, and the chairs and the chains, as they spin faster and faster, they move out into a bigger and bigger circle, and the rider feels more and more of a tilt and a sensation of fun, spinning around in a circle.
Let's analyze this situation with our force diagram. Here is one of the chairs on the ride. Before the ride is spinning, the rider is at rest, no acceleration in the x or the y direction. So in the y direction, the sum of the forces in the y is equal to 0. And t is in the upward direction, weight is in the downward direction, and I see that the tension in the chain is equal to the weight of the person. But once the ride begins to spin, now the y component of the tension is equal to the weight because there's no acceleration in the y. And the y component is equal to t cosine theta, where theta is this angle with the vertical here. So solving that for t is equal to the weight divided by cosine theta. So as theta begins to increase, as the ride spins up and the rider moves outward into a bigger circle, theta increases. So the cosine of theta decreases, and since that is in the denominator, this fraction as a whole increases. So we see as the ride spins, the tension in the chain increases. The y component is always going to be equal to the weight, and the x component now is what provides the centripetal force that causes the rider to move in a circle.
Here's a ride at the Santa Cruz Beach Boardwalk It's a big, giant circle that spins around. The people stand around the inside perimeter of the circle, and then after the ride gets going up to a certain speed, a big arm lifts, tilts the ride until the circle is spinning vertically instead of spinning horizontally.
At any instant during the rotation of the ride, each passenger in the ride has a tangential velocity. I've shown it at 4 different locations here throughout the rotation. And if magically somehow the wall of the ride were to disappear, people would fly out from the ride in a direction tangent to the circle. Of course, that doesn't happen because the wall of the ride is in the way. And so the wall of the ride pushes in on each person with the normal force. And the normal force is normal or perpendicular to the velocity and points towards the center of the circle. Here I've drawn 2 force diagrams, one for being at the top of the ride and one for being at the bottom of the ride. I read on the website for the Cyclone that on this particular ride you feel a normal force at the bottom of the circle as if you were 3 times heavier than normal. In other words, you experience 3 Gs. If you do the math, you'll figure out that that means at the top you feel a normal force that is about the same as your weight. In other words, you feel the pressure on your back against the wall just the same as if you were lying on the ground. But at the bottom of the ride, you feel 3 times your normal weight, 3 Gs. And so part of the excitement of this ride is that while you're rotating in a circle, you feel changes in the normal force of how hard you're being pressed against the wall of the ride. Not to mention the visual effect of seeing everything around you spinning in a circle. Mathematically, we see here at the top, the normal force is mv squared over r minus mg, and at the bottom, it's mv squared over r plus mg. So we see that the normal force is in fact greater at the bottom of the circle than it is at the top.
I said that if the wall of the ride were to magically disappear, people would fly out tangent to the circle. I found some examples that demonstrate this, so let's take a look at them. Here I've turned my bike upside down, and I'm spinning it around the tire, and then I'll take my hose and spray water on it, and you can see when I freeze frame the video, you can see where water leaves the tire. The water flies away from the tire in a straight line tangent to the circle. Here an astronaut is aboard the International Space Station in a weightless environment. He places a wind-up toy car in a circular track. As it zooms around the circle, the track's normal force provides the centripetal force that makes the car travel in a circle. When he separates the track, the car leaves the circle and travels in a direction that is straight and tangent to the circle. Watch what happens to these adventurous yet less than intelligent teenagers as they lose their centripetal force while moving rapidly in a circle. Let's take the example of a pendulum, and if I raise the pendulum to a height right there, a height that is equal to the length of the string. In other words, I'm going to raise it so that the string is parallel to the floor before I release it. Then when it reaches the bottom of the swing, here's the force diagram down here. We see the tension in the upward direction, the weight of the object is in the downward direction. So let's use Newton's second law for circular motion that says the sum of the centripetal forces is equal to mass times the centripetal acceleration. So the sum of the forces is T in the positive direction. We'll choose the positive direction to be toward the center of the swinging circle. And that means the weight then is in the opposite direction, and centripetal acceleration is equal to v squared over r. How fast will the velocity be here is the question mark. Okay, so we know that up here I have potential energy is equal to mass times gravity times height, and conservation of energy tells me that when it gets down to the bottom, the kinetic energy at the bottom will be 1/2 mass times velocity squared. So let's PE at the top equals KE at the bottom. So that's mgh equals 1/2 mv squared. The m's will cross off, and I'll solve this for v. 2gh equals v squared, but I'll take the square root of both sides. But we already said that the height of the ball is equal to the length of the string, so that's the square root of 2gl is equal to my velocity at the bottom. Okay, so let's go back and say that this velocity here is equal to the square root of 2gl. And over here, the length of the pendulum is the radius of the circle. So this r then can be replaced with L, and T minus mg equals this. When I square this, this becomes 2gl over L times m, and that just becomes 2mg, and T minus mg equals so I see that the tension in the string is going to be equal 3 mg. In other words, it's going to be 3 times the weight of the object. So here I've set up my Logger Pro software. That's what you see over here on the left, and it's connected on the screen on the right. It's connected to my force sensor, and from the force sensor I'm hanging a string with a mass at the end, and the force sensor tells me that I have over here on the left side the force is approximately 5 newtons. It's a 1/2 kilogram mass. So what I'll do is I'll raise the weight so that the string is parallel to the floor, and I'll release it, and over here on this left side, Logger Pro will create a force, which is the tension in the string, force versus time graph, and we can see what the tension in the string is at the bottom of the swing. Is it going to be 3 times the weight of the mass? So we expect it to be about 3 times 5, or 15 newtons. So here we go. Let's collect the data. There we go, and I need to auto scale the graph, and here we see our greatest point of tension. Follow that over to the y-axis, and there we go. There's our greatest point, and it is just a little over 15 newtons. So it is in fact 3 times the weight